right, let's now move on to some of the facts, some of the approximations, okay? Now, if you remember, I gave you this, we learned from the above slides that emitter current is going to be equal to IC plus IB, okay? We understand that IB, which is the base current, is going to be very small, okay? Okay, so remember, this is a schematic of the transistor. This is a schematic symbol of it, okay? If I have an arrow like this, that means the current flows from positive to negative. So this is going to be positive, this is going to be N, and therefore this is going to be N. So it's a NPN transistor, NPN transistor. Okay, all right. This is the base of the transistor, base. This is the emitter terminal of the transistor, and this is the collector terminal of the transistor. So you have current flowing into the base, okay, we refer to as IB, okay. Then you have this current IC, collector current, and these two current, then they flow into the emitter terminal, IE. So if you apply KCL, if you consider it as a node, you have IC coming in here, you have IB coming in here, they combine and give us this equation, correct? Everybody following me here? Base current being very small, in microamps, okay? So I can also write down this above equation, IE approximately equal to IC, okay? And that's how we get to this point here. Base emitter voltage, this is also written as VBE, okay? But VBE would mean base emitter voltage. This is also equals to VB minus VE, okay? Similarly, VCE would mean this is the common collector emitter voltage, okay? This is usually the output voltage. And this VCE is equals to VC minus VE, okay? You don't have to memorize this. The easiest way, that's how I learned it. If you look at the subscript, it's B and E, right? So therefore you have VB minus VE. Similarly, if you look at the subscript here for VCE, you will have VC minus VE. So you don't really have to memorize this. Again, if you're looking at VCB, then VCB will equals to VC minus VB. Okay, cool. This base emitter voltage, if the transistor is made up of silicon, is always going to be 0.7 volt. That is just constant. Okay, it's not going to change in any of our analysis that we will do. Okay, so just keep in mind that VBE is the base emitter voltage, and it's 0.7 volt. So you have the base terminal here, correct? You have the base terminal, you have the emitter terminal. The voltage between these two terminals is referred to as VBE. It is 0.7. So that is inherent to the transistor. And the transistors, when you buy the transistor, they'll come with a data sheet and they will tell you what is VBE. It is usually 0.7 because they are made up of silicon. Okay, let's move forward. I hope everybody's following me here so far. Okay, alpha, what is alpha? Alpha is a ratio of IC to IE. Remember, IC is the collector current, okay? And then IE is the emitter current, right? Okay, the alpha is going to be a ratio of the IC over IE, okay? And because we know that IC is approximately equal to IE, so if I say IC over IE, because IE is equals to IC, so I can say IC and IC will cancel out and I get 1. So therefore, ideally, alpha is going to be 1, but in reality, it is going to be 0.9 to 0.998. Okay, very close to 1. Okay, so something to remember. And remember, this is in a DC mode because we can apply a DC voltage to a transistor, but also we can apply most circuits. We might not do that circuit today, but Tuesday we'll do that circuit when we do signal analysis. The signal analysis would include AC and DC both. For today's lecture, we are mainly focusing on DC part. Okay, if in a AC mode, then alpha is basically change in collector current, okay, ratio of change in collector current over change in emitter current. Okay, all right. Transistor amplification. Here's one quick problem here. So we have been given an input signal, which is 200 mole. That's the peak value. Okay. The input resistance is 20 ohms. The output resistance is 100 ohms. There's a load resistor, which is 5 kilo ohms. And this is a PNP transistor, right? This is a PNP transistor. Here's the emitter terminal over here. Okay, this is your emitter terminal, this is your base here, and then this is your C here. Okay, all right. Now, how they are measuring basically they want to get an idea like how much would be the voltage gain. So because this is amplification here, so you would think, you have a 200 millivolt signal. Hopefully it will be amplified, but how much time it is amplified, that is what we are trying to find out here. Okay. Now let's find out the emitter current, which is current flowing into the emitter terminal of the transistor. So just simply apply Ohm's law, which will be VI over RI. VI is 200 millivolt, correct? So I got 200 here. RI is 20 ohms. So that's where you plug in those values. If you do the math, you get IE equals to 10 milliamps, correct? We also know from our previous analysis that IC collector current equals to emitter current. Therefore, I can also write it down that this current, which is labeled as IL, is basically my IC current. Okay, and because IC is 10 milliamps, so IL is also going to be 10 milliamp. And then because I know this current, which is IL flowing into this load resistor, is 10 milliamps, I can simply apply VL equals to IL times RL to find out the voltage across this load resistor. So when I do that, I plug in these values, I get VL, which is 50 volts. Now remember, this 50 volts over here is the voltage across this resistor, okay? And this is basically the output voltage, correct? I can extend that to something like this and say this is the output voltage, or VL, same thing. Okay, now the gain, we know the gain is what? The gain is the output voltage over input voltage. The output voltage came out to be 50 volts, so you put 50 here. And then the input voltage was 200 millivolt, correct? 200 millivolt. You do the math and you get 250. And that basically tells you that this signal over here is amplified 250 times as much as the input voltage over here. Okay, so this is basically just how the resistance is working. With the reverse bias, we set this value for the resistance high, and with this forward bias, we set this value of the resistance very small, and thus we are able to increase the voltage, the output voltage, and that gives us the higher gain. Okay,